Okay, so we have a new classroom. You like it, or do you want the other one better? Yeah, that one is hot. I think I heard that this one, we are the only one using this classroom. So 4 hours. Properties of a system. Property is any characteristic of a system such as pressure, temperature, mass, volume, energy, or anything, okay? And there are many properties for a system. However, there are 4 main properties that we are going to study in thermodynamics. They are pressure, temperature, volume, and mass. Among these properties, some are intensive properties, the others are extensive properties. Intensive properties are those independent of mass, so such as temperature, pressure, or density, or any specific properties. How do we know whether they are intensive properties or extensive properties? You can simply try to divide that property by mass. If it makes sense, then it's an extensive property. If it doesn't make sense, then it is an intensive property. For example, temperature. Can we divide temperature by mass? Mathematically, yes, but what does it mean? It means nothing, right? What about the temperature of your body and temperature of my body? Even though we have different weights, we have the same temperature, right? So we cannot divide temperature by mass. So temperature is an intensive property. What about pressure and density? We cannot divide them by mass. So they are intensive properties. On the other hand, if you can divide a property by mass, then it is on extensive properties, such as mass, volume. If you divide volume by mass, it becomes specific volume, which is the inverse of density. And energy. If you divide energy by mass, it becomes energy per unit mass. If you divide momentum by mass, it's going to be momentum per unit mass. So which makes sense, right? So those are extensive properties. Now the problem is going to be, if you want to use energy balance equation, mass balance equation, or momentum balance equation, you do not want to mix intensive properties and extensive properties because they are different, right? So we want to stick to one. Let's say we can only use extensive properties or intensive properties. However, the problem is that if you have an intensive property, sometimes it doesn't make sense to convert this intensive property to extensive property. For example, temperature. If you want to, convert this temperature to extensive property, you can multiply by mass, but mass times temperature doesn't mean anything in science. So we prefer to use intensive property over extensive property when we solve a governing equation. Then how can we use only intensive properties? Because sometimes we have to use energy, volume, mass. Then we can simply divide them by mass and then use them in an equation. Okay? So that we can only use intensive properties. Those extensive properties that are divided by mass are called specific properties. So if you divide energy by mass, it becomes specific energy. If you divide total volume by mass, then it becomes specific volume. If you divide anything, any extensive property by mass, it becomes specific property. So if you hear specific in front of a property, then you can assume that it's going to be that property divided by mass. So per unit volume. Then in an equation, when we solve any equation in thermodynamics, we are going to use either intensive property or specific property. Then what about, if I want to calculate the total energy of a system? You can use specific property and intensive property. Then at the end, you can multiply by the total mass of the system that give you the total energy. Okay? So that's what we will do. We have many practice problems in during in each PowerPoint. So while we are solving them, we will see how we can use intensive properties and specific properties. Okay. Then let's talk about some specific properties. The first one is density, mass per unit volume, and which is pretty common. We have pretty good knowledge about what is density. In thermodynamics, we prefer using specific volume. Specific volume, density, they mean the same thing. It is the density is mass per unit volume, and specific volume is volume per unit mass. So the density is the inverse of a specific volume. By the way, when we talk about extensive property, such as volume, such as energy, so volume, we use capital V. If it is energy, we use capital E. If we divide them by mass to use specific properties, divided by mass, and to distinguish between volume and specific volume, we use lowercase. So when you see a lowercase such as V or E, you can see that's not a volume or energy. They are specific volume, specific energy. So if you want to get volume and energy, you can multiply them by mass. That will give you total energy, total volume. Okay. So the specific volume in this case, lowercase v, is the actual volume divided by mass. The unit is going to be cubic meters per kilogram. Another important property is the specific gravity. Specific gravity is the ratio of the density of a substance to the density of some standard substance. Usually we use water for this standard substance, water at 4 degrees Celsius. Why do we use water at 4 degrees Celsius? Because its density is pretty simple. The density of water at 4 degrees Celsius, which is 1,000 kilogram per cubic meters. Very simple, right? So we use this for the standard substance. So specific gravity is the ratio between our system and the density of water. So if the specific gravity is 2, you can multiply this number by 2,000. If the specific gravity is 10, you can multiply it by 10 times. And there are common materials that we use in terms of specific gravity is mercury here. Its specific gravity is 13.6. We will see this number quite often later when we study pressure. Finally, specific weight, the weight of a unit volume of a substance. So it is density times gravity. This density times gravity, you will see this one often when you study fluid mechanics or pressure at the end of this chapter. So we will talk about that later. Okay? Any question about this slide? Isn't it still hot, right? No? Good? Better than the other one, right? My first job was a professor at in a university in Texas. Hot. But the buildings usually have a pretty good air conditioning. One day, I taught a class that has about 70 students enrolled in that class, and the classroom size about this. So there are about 30 students sitting on a desk, the 40 of them standing in the back. Imagine how hard it is. Then I decide I need to go up north. I found this one. It's getting hotter and hotter and hotter, the year by year. And I need to find a place in Canada or something. Isn't the summer here is hotter than the last year, isn't it? Question? Okay, yeah. Actually, you can use either 4 degrees Celsius or 0 degrees Celsius because the density of water, the reference, is the same, 1000. Yeah. Usually, the density of solid or liquid do not change depending on pressure. Only gas changes its density because gas the continuously deforms, right? So usually in practical engineering, we assume that the density of the liquid or solid are going to be the usually constant. We expect that they are incompressible, which meaning is that the volume is not going to change in a common environment unless you are studying something extremely high pressure or extremely low pressure. Okay. Yeah, I didn't know that. 4 degrees Celsius. Yeah, that's a good catch. State and equilibrium. Equilibrium is a state of balance. So if you look at this sphere right here, you can see so once the change a property of a system, or once you provide heat or remove heat, provide work or remove work from a system, initially it is possible that there are the heterogeneous distribution. So sometimes that there's a 20 degrees Celsius here, 40 degrees Celsius here, 35 degrees Celsius here. If you leave it for a certain time, that there will be thermal equilibrium, which means that either they have the same temperature. Our assumption is that that when we solve a thermodynamics problem, we assume that our system meets thermal equilibrium. Okay, so when we say that this coffee is at the 90 degrees Celsius, maybe initially when the people pour coffee inside, there will be 91 degrees Celsius, 89 degrees Celsius. But if you leave it maybe 5 to 10 seconds, then it will have a thermal equilibrium. Our the assumption when we solve any energy balance equation or mass balance equation, our assumption is that it has a thermal equilibrium inside. Okay. Then what about I want to study the heat transfer between 20 degrees Celsius here and 40 degrees Celsius here. Can we solve that kind of problem in thermodynamics? Yes, we can. If you want to the study, so what happened is that initially there was a 20 degrees Celsius at the top and 42 degrees Celsius at the bottom. We assume that there will be heat transfer from the bottom to the top so that, it meets the thermal equilibrium. So let's say, oh, I don't want to assume thermal equilibrium in this system. I want to study how much heat transfer from 42 degrees Celsius to 20 degrees Celsius. Can we solve a problem, something like that? Yes, we can. Instead of having, this as your system, you can, select, oh, this is my system. Then the surrounding is going to, and these are going to be the surroundings. Then you can study heat transfer from the surrounding to the system. So it all depends on how you define a system. So sometimes you can define the entire, the chamber as your system, or sometimes, define it. So it all depends on how you design the problem. So there's nothing we can calculate in terms of the energy in thermodynamics. So our understanding, our assumption is that, that whenever we have a system trying to solve, the system thermodynamically, our, the assumption is that the system is in thermal equilibrium. Okay. Then process. So let's assume that, that we want to study the heat transfer from this coffee to the surrounding air. So I'm actually, increasing the air temperature in this classroom by having this coffee. So what happens is that there is a heat transfer from the coffee to the surroundings. So let's study that thermodynamically. So we have this cup, and we have a coffee inside. This is red. Doesn't look like coffee. I have a brown here. Okay. Okay, so there's a coffee, cup, and the surrounding air. So in this case, this coffee is going to be our system. The surrounding air. So air is everywhere. So, but the simplicity, we are going to, assume that air is only on this side. Otherwise, if I want to, to say there's a heat transfer, I have to, draw arrows in every direction. So I'm going to say there's a heat transfer from this coffee to the air. And this air is going to be what? Its surroundings. Then this cup is the boundary. So if you want to study, the heat transfer from the coffee to the surroundings thermodynamically, this is how you design system, boundary, and surrounding. Then let's talk about thermodynamics. What kind of, thermodynamic problem we can, think of. So we can say initially the temperature of the coffee was hot, and after this class, the temperature of the coffee went down. Let's say from 90 degrees Celsius, initially 90 degrees Celsius, the surrounding air is at 20 degrees Celsius. After 1 hour, the temperature went down to 60 degrees Celsius. Then this is a heat transfer process. Initially, it was 90 degrees Celsius, and at the end of this heat transfer process, the temperature of the coffee is going to be 60 degrees Celsius. So 90 degrees Celsius is state number 1, starting initial state. And this is a cooling process, so heat is removed. During this cooling process, the temperature of the coffee became 60 degrees Celsius, state number 2. So this is the initial state, this is the final state, and the process is going to be cooling process. So what we can see here, whenever there is a process, whenever there is one process, how many states do you need? 2. Initial state and the final state. Okay? So process, any change that the system undergoes from one equilibrium state, the initial state, to another equilibrium state, which is the final state. So whenever you have a process, you need 2 states. When you have 2 processes, you need 4 states? No, 3 states, because initial state, 1 process, second state, another process, third state. So if you have 2 processes, you have 3 states. If you have 3 processes, you have 4 states. Pass the series of states through which a system passes during a process. Oh, yeah, and then, quasi-static, quasi-equilibrium process. When a process proceeds in such a manner that the system remains close to an equilibrium state at all times. That means that, that when we say temperature of the coffee went down from 90 degrees Celsius to 60 degrees Celsius, our assumption in thermodynamics is initially everywhere in the system is going to be 90 degrees Celsius. Maybe 2 minutes later, everywhere in the system is 88, 86. So we assume that the system temperature goes down while maintaining thermal equilibrium. Okay? Then there are 3 common processes that we are going to study thermodynamics. The first one is isothermal process, which means that temperature remains constant. The second one is isobaric process, a process when pressure P remains constant. Isochoric process, a process when the volume V remains constant. So in thermodynamics, there are many, the properties are, related to each other, but there are 3, the common properties that we are going to study thermodynamically. They are pressure, temperature, and volume. So let's assume that this is a water bottle. This is not a water bottle, so you don't want to drink inside. But let's assume that this is water bottle. So if you squeeze it, what happens? If you squeeze it, its volume goes down, right? So that means that when you squeeze, what does it mean in thermodynamics? We will increase pressure. So when you squeeze it, you increase its pressure. Then what happened to its volume? If you squeeze it, volume goes down, right? It looks reasonable. In reality, and so can I say like that? If you increase pressure, volume goes down. No, you can't, because you have no idea about temperature. While I'm squeezing, maybe the temperature of the the liquid inside goes up. So it may increase the volume, right? So you cannot say, that when pressure goes up, what happened to this volume? The only way you can explain this phenomenon is that, when temperature is constant, when pressure goes up, volume goes down. So when you squeeze it, you can see the volume goes down because the temperature of the liquid remains constant. What about the temperature of the liquid inside goes up or goes down while I'm squeezing? Then we don't know what is the final temperature. We can only know the final temperature when we assume that temperature remains constant, because we have no idea about how temperature changes. But you can say when temperature goes down and pressure goes up, then the volume goes down. But unless that we have information about temperature, you cannot say what happened to the volume when pressure changes. So the simplest way to understand this thermodynamics the phenomenon is we fix one property. So let's assume that temperature is constant. Temperature is constant. Then when pressure goes up, volume goes down. Or pressure goes down and volume goes up. That is constant temperature process, or in other words, isothermal process. So that's one of the processes that we are going to study. Another one. Instead of temperature, we can assume constant pressure process. Then what happens when the temperature goes up? What happened to the volume? When temperature goes up, volume goes up. Temperature goes up, volume goes up. Did you see such a phenomenon? Yes, about 2 or 3 weeks ago, there was a festival in Midland, balloon festival. So people do these kind of things and go up the sky. And how can they go up? They increase the temperature inside this balloon. So its volume goes up. The volume goes up means that its density goes down. So it becomes lighter so they can fly. Okay. And the last one is constant volume process. Now, if this one is constant, then we can understand what happened to the temperature when pressure goes up. When pressure goes up, temperature goes up. When pressure goes down, temperature goes down. So if you make one property constant, you can expect what happened to the other. Okay, that's why we study isothermal process, isobaric process, or isochoric process, because without these assumptions, a problem can be very complicated, right? So this is a way to simplify a system. Our cycle is a process during which the initial and the final states are identical. So usually cycle consists of several processes. So process number 1, pressure goes up this much. Process number 2, pressure goes down this much. And process number 3, and then go to the initial state. Then these 3 processes become one cycle. Okay. We are going to study cycle later, when we go to chapter 8 or chapter 9, when we study Rankine cycle, Otto cycle, and gas turbine, etc. Okay. By the way, if you have any question, please, interrupt the middle of the class. The next one is steady or unsteady. Steady process means a process which is independent of time. That's a steady process. Unsteady process means time-dependent problems. So let's go back to this coffee problem. So there's a heat transfer from this coffee to the surrounding. Is it steady process or unsteady process? Unsteady process because it's time dependent. How do we know whether it is time dependent or time independent? You can see whether the property of this coffee changes in time. So initially, what was the temperature? 90. After a process, after this cooling process, what is the temperature? 60. So you cannot go back 90. So it's a time-dependent problem. In this course, we are going to study either steady process or unsteady process. In chapter 3, oh, I was writing here. In chapter 3, we are going to study a closed system. And closed system, especially unsteady process. In chapter 4, we are going to study an open system, which is usually steady process. Okay. And the maintaining a steady process, which is very important, like the air conditioning system in this classroom, is a steady process or unsteady process. What is the system when we want to study that air conditioning system? What is our system? Yes, air is our system. And what is the main property of air when we run the air conditioning system? Yes. Should it be constant or variable? We want it to be constant. So we can have, that's why we run the air conditioning system. Please make sure that the temperature here is going to be 70 Fahrenheit. Never change. So when temperature does not change at 70 Fahrenheit, it's a steady process. When it goes up, like the other room, that's unsteady process, right? Then, is it always steady or unsteady? When you have an engineering device, it can be either steady or unsteady. So let's think about one example. What is the most common, the engineering device you have? A car. Okay, so let's say there's a car. So if you sit in front, sit in the driver's seat, what do you see in front? Nice view? No, as an engineer, you will see this front panel, right? So there are two, kind of old one, right? The new one has many, the fancy things. Mine has this too, okay? So the left-hand side, it says MPH. No, RPM. The right-hand side, it says MPH. So what this RPM means? What is this gauge means? Right. That means the how fast your engine runs, right? What about this one? That means how fast your car runs, right? So these are the two gauges that you see often. However, there are more important gauges. The one gauge saying that E and F. I think this is the only time that you like this letter F, right? No? We hate this letter, you know, in school, right? But you know, when you look at your car, you know, you like this letter, right? And there's another one, CNH. What is the most important gauge here? This one? This one? This one? Let's think about that. Maybe this one. What is the risk factor? So if you go beyond a certain limit, 200, yeah, you pulled over. That's the risk factor, right? So you may be paying about 200, 300, depending on how many you get rewarded, right? So that costs a lot of money, right? What about this one? If you go to here, then maybe depending on the market, depending on gas market, it changes, but usually $50 or $60. So that is less important than this one, right? What about here? So there are some numbers: 1, 2, 3, 4, 5, 6, 7. Oh, if it goes up, then your mileage goes down. So you want to maintain the somewhere in the low range, just to make sure that you don't consume too much gas. So that's somewhat important. Many people don't even look at this one. However, this is the most important gauge, because you usually see at the beginning when you just start your engine, it was pointing C, right? It means that the engine has no heat inside. So while you are running, we call it warming up, right? While it is warming up, this gauge goes up. What does it mean thermodynamically? Unsteady process. And after 5 to 10 minutes, you see it is, the pointing right at the center. That means steady state. So when you're driving your car to come to the campus, initially your car is unsteady process and becomes steady process. And you want to make sure that you want to, have your car to be steady state until you finish driving. But sometimes, once in a lifetime, you see this one goes up. Unsteady process. So how much is it going to cost? It depends on the car, maybe $30,000 to $50,000, right? Because you need to buy a new car. So when you see your car doesn't go, the steady stop process, it means that it's okay. Today is the day I'm going to buy a new car, right? So that one is most important process. So that shows unsteady and steady. You can see steady process means that the main property of the system does not change. In this case, the coolant temperature. Okay. The zeroth law of thermodynamics: if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. You can just go through that and you can easily understand that. Okay. Any question about this slide? No? I think we can move on. Temperature, we are going to study two properties in this chapter 1. The first one is temperature, not very fun. The other one is pressure, which can be slightly, more interesting. Okay, so let's finish this temperature as fast as we can. Okay, but there's nothing, nothing very difficult here. It is about, what is the SI unit, what is the SI temperature unit, and what is the English unit of temperature, how we convert, and things like that. Oh, what is the reference material that we studied in this chapter in terms of, a property? We discussed specific gravity. What is the reference, the material? Water. So water can be, the reference material when we determine temperature. So there are two temperature units and two temperature points. One is ice point, the other one is steam point. And in degrees Celsius, ice point is going to be 0 degrees Celsius. In steam point, it's going to be 100 degrees Celsius. On the other hand, in Fahrenheit, the ice point is 32 Fahrenheit, steam point is 212 Fahrenheit. So, okay. So can we say the steam point of water is 100 degrees Celsius? Is it true or not? When I say like that, it sounds like it's not true, right? So the answer is it's not true. You can only say the steam point of water is 100 degrees Celsius when the pressure is 1 atmospheric pressure, because temperature, pressure are related. So do you remember we discussed this one, right? So those, the thermodynamic properties are all related. Steam point changes with atmospheric pressure. So what is then isn't it that the boiling temperature of water is 100 degrees Celsius in Mount Pleasant? In Mount Pleasant, yes. Anybody from Denver, Colorado? No one. So, but if you go to Denver, Colorado, it is not. The atmospheric pressure is way less than here, because if you go up, you have, the less air, right? No. Yes. If you, take, the airplane to go to where? Where do you want to go during a vacation? Greece? That's too far. I want to be, somewhere in 3 or 4 hour range. Florida, yeah, Florida sounds good. Okay. So if you fly to, the Florida, the airplane goes up, and it stays at a certain, the altitude. What is that? About 30,000, the feet or something, right? And it lands, when you go to, the Florida. What about if you take a private jet? So you're one of the rich guys, and your name is pretty popular in stock market. Then is this private jet go to the the 30,000 feet? Stay there like a commercial jet? No, goes down or goes up. I don't know why I talk about this one, but it's fun. Okay, so do you go up or go down? Down. How many do you think that the private jet goes below the commercial the jet? How many of you think that it goes above? What about at the same? The answer is usually. It's also the personal preference, but most of them, more than 99%, I think 100%, they go above. The reason is that if you go above, you have much less air. So your airplane is going to be very quiet. No shaking or something. You have much less air. Then the question is, why commercial jets doesn't go above? Because if you go above, there's a less amount of air. So your fuel consumption goes up. So you spend much more fuel. So you don't go up. You stay there. So we have a certain amount of air. So we can, burn, the limited amount of fuel, but we can fly. But if you're driving private jet, do you care about, the fuel consumption? No, I don't want this shaking in the airplane. I want, the quiet, the journey. So you go as far as you can and go up there. There's nothing. You cannot hear anything. There's a very limited amount of air. I don't know why I talk about that, but you can get the idea that, when you go up, you have less amount of air. So if you go to Denver, Colorado, the amount of air is less than, here. That means that the pressure, the atmospheric pressure is less than here. Usually, I'm not sure the exact number, but the atmospheric pressure, if you assume that the atmospheric pressure in Mount Pleasant is approximately 1 atm. By the way, 1 atm means the pressure at the sea level. So if you go to Florida, near Miami Beach, the pressure is going to be 1 atm. Mount Pleasant is about the same altitude, so not much. So it's almost 1 atm. But if you go to Denver, Colorado, because they have on top of mountain, so it has less air. So I'm not sure, but it's about approximately 0.8, the atmosphere or something. So they have less air, the atmospheric pressure is less. So their boiling point, the steam point is less. It's usually 92 or 93 degrees Celsius, depending on the, the outside pressure, which is less than 100 degrees Celsius. Okay. So what it matters, if you go there, if you cook pasta at the same time, like, according to the instruction, the back of this pasta, the box, it says that cook it for 5 minutes. If you cook it for 5 minutes in Denver, Colorado, it's going to be undercooked. So you need to cook it, the 6 or 7 minutes, because it boils at lower temperature. Therefore, less amount of heat goes into a noodle. How do you say noodle is cooked or not? So noodle need to receive enough amount of heat so their chemical bondings between carbon, hydrogen, oxygen changes. So you can say it's cooked. When you cook steak, it's a red meat, and after it becomes brown. Why the change? Why there is a change of color? Because the carbon, hydrogen bonding has been changed. So you have a different thing. Red meat and brown meat. It's cooked. So if you want to cook something, you need to provide this amount of heat. But if the temperature is less, boiling temperature is less, you provide less amount of heat. I don't know why it become cooking class, but you get the idea. You get the idea. When pressure goes up, temperature goes up. If the atmospheric pressure is high, then the boiling temperature goes up. That's how we use pressure cooker. If you go to Target or Walmart and buy Ninja pressure cooker or something, you can cook it faster. Why is that? For the same water boiling, because we use water boiling a lot in cooking, for the same, the boiling of water, you provide more heat into the food. That's why, that's how you, expedite, the speed up the cooking process. So that's pretty much everything about ice point and steam point. Celsius is in SI unit system. So 0 degrees Celsius is, the ice point at 1 atmospheric pressure, and 100 degrees Celsius is a steam point. On the other hand, in Fahrenheit, they are 32 Fahrenheit, 212 Fahrenheit. So you can get the idea how you convert between Celsius and Fahrenheit. In Celsius, the ice point is 0 degrees Celsius and the steam point is 100 degrees Celsius, assuming that it is 1 atmospheric pressure. On the other hand, in degree Fahrenheit, it's going to be 32 degree and 212 degree. So what is the ratio? Here, the difference in temperature is going to be 100. Here, the difference in temperature is going to be 180. So the ratio between Celsius and Fahrenheit is going to be 100 to 180, which is 100 over 180, which is approximately, not approximately, exactly 5/9. So if you want to convert between Fahrenheit and degrees Celsius, this is the value you can multiply. 5/9 or 9/5, this is the ratio. So let's say that I have a degree Celsius. If you want to convert into, the Fahrenheit, you can multiply by what? 9/5. However, we have a different starting point. The starting point is 0 for Celsius. Fahrenheit is 32. So you need to add 32. Add 32 Fahrenheit. That becomes, that's how you convert. If you want to calculate, the degree Celsius from Fahrenheit, you can go reversely, okay? Or you can ask ChatGPT or Gemini. Don't ask. We are engineers studying thermodynamics. You know how to convert, right? I'm sorry. Oh, by the way, between Celsius and Fahrenheit, which one is the standard SI unit? None of them. None of them. Yeah, Kelvin, Kelvin. Well, then what is English? What is the standard English unit? Fahrenheit or Celsius? You just the heard from the previous example. None of them. So Kelvin, Kelvin is the standard SI unit for temperature. Rankine, had you heard about that? Rankine is the standard English unit. Then let's talk about why Kelvin is that. Why it is a standard unit. I think Celsius is good enough because it is based on science. 0 degrees Celsius for ice, 100 degrees Celsius for the water boiling. Then why we need to use another the SI unit, another the unit for standard SI unit. And then by the way, how you calculate this Kelvin? Calculating Kelvin is one of the easiest one in thermodynamics. So you have a degree Celsius plus 273.15, it becomes Kelvin. Oh, some people say 273.16. And do we care as an engineer? No, no, no. Just 273 is fine. If you want to the study 273.15 or 16, you can go to the science department over there. Some people may question that why don't we care about those small decimals? They are important. Yeah, they are important. However, we as an engineer we need to think about our practical application. In practical application, what we deal with energy, heat, and controlling heat and energy. Yes. In the classroom, we only use SI unit, so you won't see Rankine scale. In your homework, you maybe, because you need to get used to the playing both units, but to be consistent in the classroom and exam, and classroom, we only use Kelvin. No, not necessarily. We use Kelvin and Celsius. So in practical application, the heat transfer comes with a lot of errors because measuring, the heat, measuring energy is very tricky. Even, the people, in the laboratory and doing, a lot of researches, they make a lot of mistake, the measuring, the heat capacity, specific heat. So the effect of those errors is much, much greater than these, the small errors in this calculation. So neglecting this one doesn't affect your research. If you go to science department, that matters because we don't care about money, but in engineering, we care about money, right? So we are putting science and, the business together, right? That's what engineering, the engineers do, right? That's how, that we increase our pay grade compared to science department. No offense, but we are all science, right? We are all engineering, right? None of you are from science, right? Okay. Off the record. Just trying to make this class fun, okay? Don't get offended, okay? So, but usually, we neglect those small, the differences because they don't matter. When we, like for example, if you want to build this building, let's say to maintain the second floor doesn't collapse, we need to have, about this much size of, the pillars and walls to be built. So we stick to that? No, we double or triple, just to be safe, just to be safe. So do we actually care? Is it should be 23.567 inches, or we can just say 24. In engineers, we say, oh, 24 should be enough, multiply by 3, and then build it, and it never collapses. In business speaking, That's no problem. 23.456 and 24. There's no difference in business, but in science, it may matter, right? Because if you say 24 inches, maybe we can study one day. But if you want to exactly calculate 23.456, you need to spend a year. Are you going to spend a year to correct that mistake? No. Okay. So in your exam, this one is okay. If you want to add them, that's okay, right? I didn't, discuss why we use Kelvin. So if the room temperature is 20 degrees Celsius in Kelvin, it's going to be 293 Kelvin. So the temperature in this classroom is 293 Kelvin. Then if the temperature is 0 degrees Celsius, you can say it's going to be 273 Kelvin. What about minus 100 is going to be 173 Kelvin. What is 0 Kelvin? That's absolute zero. What is the temperature in degrees Celsius? 273 degrees Celsius. This is the temperature. We assume that there is no thermal energy left over in the system. So if you watch a science movie, it says that, oh, we just went to a space whose temperature is minus 500 degrees Celsius. It's possible or not? Impossible. The lowest possible temperature is this absolute zero. Now, we get the idea. Okay, Kelvin means something. So maybe we can use this one as a standard SI unit. So that's everything about temperature. Any question? Temperature? No. Now, the last one. Pressure. So, if you kind of, the board about the previous, the materials covered in chapter 1, now this is time you can enjoy. Pressure is somewhat fun, okay? So, variation of pressure with I was reading something else. Pressure is a normal force exerted by a fluid per unit area. Then why we use pressure? It's simple, because pressure is force by fluid. What defines fluid? Something flows? Yeah, you're right. So the definition of fluid is that the material that continuously deforms. So if you have a cup, the fluid can have any shape. It has the same shape as its container. So if you pour into another cup, the shape of the fluid is going to be that shape, right? So if you have a fluid, because it continues to deform, you cannot, you cannot, say there's a force by fluid at this point, on this way. It's not possible because it continues to deform. So when we talk about force by fluid, we talk about the entire, the surface area. So we assume that when the fluid is, the touching, this surface, then we, to discuss that force, we use pressure acting on the entire surface area. Then how can we determine, the pressure? Simple. Pressure is force divided by the area where, the fluid is, the covering. That's pressure. What is the unit of force? Newton. What is the unit of area? Meter square. So pressure is going to be Newton per meter square, and we have a new unit, Pascal. However, Pascal is pretty small. It's very small. So we usually, use kilopascal. 1 kilopascal is 1,000 Pascal. What is the atmospheric pressure? At the sea level, 1 atm is 1 atm is 101,325 Pascal. So 1 Pascal is very small number. So we generally use kilopascal or megapascal. So in kilopascal, 1 atmospheric pressure is 101.325 kilopascal. And some people like to use, the another pressure unit, which is bar, not the bar that we drink, right? 1 bar is 100 kilopascal. So 1 bar and 1 ATM is very close to each other. Not exact number, but close to each other, okay? So sometimes, you see, the bar in a property table. Sometimes you see kilopascal or, the megapascal in a steam table. So we may use both. Don't get confused between them, okay? And there's another unit. Sometimes, the people use millimeter, the HG or inch HG that we will talk about that later when we talk about barometer. So these are the pressure units that we are going to use in thermodynamics. Okay. By the way, let me know if it is just too fast or too slow. Okay. We have 12 minutes. It's a lot of time, that I can drive home, have breakfast, and take a nap and then come back and continue to teach. So 12 minutes, we can finish the entire chapter. Okay, so absolute pressure, gauge pressure, vacuum pressure. So pressure units, there are already many pressure units, then there are many different pressure names. So let's talk about that. Absolute pressure is the actual pressure at a given position. So when I say the atmospheric pressure in this classroom is 101.325 kilopascal, that is absolute pressure. So sounds right. We just need absolute pressure. So that is the absolute pressure. Why do we need, the gauge pressure and vacuum pressure? Let's talk about that. If you go to one of the laboratories, on the other side where air conditioning is not working, there's no air conditioning over there, right? Because the building was built, the long time ago when Michigan was way cooler than now, right? So you may see, the many, the gas tanks, gas cylinders. So let's say that there's a, the one chamber, and you may see, looks like this. So it looks like measuring pressure inside, right? So let's say it is pointing at this point, let's say 200 kilopascal. So what is the pressure inside the gas tank? You can say 200 kilopascal. That is incorrect. Why is that? Because that pressure measuring device can only measure the difference in pressure between the chamber and the surrounding. What is the surrounding in this case? The atmosphere. The atmosphere. So what is the atmospheric pressure? T ATM, not the automatic teller machine. Atmospheric pressure is 101.325 kilopascal, and whatever you read from this gauge is gauge pressure. T gauge, and that is 200 kilopascal. Then what is the absolute, what is the actual pressure inside the chamber? As I told you, this one can only measure the difference between here and outside. The absolute pressure is going to be TABS, anti-braking system, right? That's 1.325 kilopascal. So this one is absolute pressure, the actual pressure. Gauge pressure is the difference between absolute pressure and atmospheric pressure, and atmospheric pressure is the outside. Okay, so you can see absolute pressure PABS is gauge pressure P gauge plus PATM. Then some people may say, oh, since the pressure measuring device can only measure the difference between the chamber and the surrounding, you can always add the atmospheric pressure and only use absolute pressure. Why we need to use gauge pressure? Because using gauge pressure is convenient when you study some subject, fluid mechanics. In fluid mechanics, when you study the fluid kinematics, you can just ignore the atmospheric pressure and only use gauge pressure. So in some the subjects, you can only use gauge pressure, and of course we need to know the actual pressure. So there are so many the pressure names. Okay. The last one, vacuum pressure. Okay, so I thought that that we already studied 3 different pressures: atmospheric pressure, gauge pressure, absolute pressure. Why we need another one, vacuum pressure? The vacuum pressure is needed when the actual pressure inside is less than atmospheric pressure. What about the absolute pressure? So it is on the vacuum. So what about the inside the cylinder? The pressure is only 50 kilopascal. So the absolute pressure is 50 kilopascal. So let's assume that it is on the vacuum. On the vacuum does not necessarily mean that there is no gas. You have less gas than outside. That's a vacuum, high vacuum, under vacuum. Okay. So let's assume that the absolute pressure inside this vacuum chamber is only 50 kilopascal. So this one is 50 kilopascal. And what is the atmospheric pressure? 101.325 kilopascal. So what is the gauge pressure? According to this calculation, it is minus 51.325 kilopascal. Can a pressure value to be positive? No. Pressure cannot be, I say positive. Can pressure become negative? No. You cannot have a negative pressure. So this is incorrect. So we have to use another equation only for the vacuum. So gauge pressure means the difference between these two. So how can we change this equation to have a positive gauge pressure? Atmospheric pressure is absolute pressure plus gauge pressure, then it becomes positive. However, to distinguish between gauge pressure and this one, we say this one is vacuum pressure. So in that case, absolute pressure is 50. Atmospheric pressure is 101.325, and vacuum pressure is the difference between these two is 51.325. So none of them is a negative value. So everything is okay. So when your system has higher pressure than the surrounding, you can use this equation. When your system pressure is less than the surrounding, you can use this pressure. So you may see only gauge pressure or vacuum pressure. You cannot see both gauge and vacuum in one thermodynamics problem. Okay? Any question? No? Oh, right here. Now, this is the most important slide in terms of pressure. So it has everything. It has all the theory. Variation of pressure with depth. So what is the driving, what is the cause of, the pressure. What am I saying? So we are going to talk about atmospheric pressure. So pressure changes in the direction of gravity. So if you climb Mountain Everest, you feel that you have a less amount of air, you have a less atmospheric pressure. So some people need to use an oxygen tank if you want to go up to Mountain Everest. Or what about if you go to the the sack, there's a swimming pool. If you dive into the swimming pool, what do you feel? You feel pressure increase when you go deeper and deeper. So pressure changes with depth. So if you go deep, then pressure goes up. If you go up, pressure goes down, because that's the gravity direction. What about if you go, the horizontally? If you go from this classroom to the hot classroom over there, the pressure does not change. The pressure only changes in the direction of gravity. Okay? Then how much pressure changes? By this much. Oops. Oh, that's interesting. By this much. Specific weight. Pressure changes by this much. Specific weight. Density times gravity. So that is how much the pressure changes. In mathematically, how do you determine, how do you say the change of a property in mathematics? Yeah, you can do that. And you can also do that in, by using gradient, pressure gradient, dP over on what direction? dx is going to be, let's assume that going above is positive. So this one is positive direction. Gravity is going downward. It's going to be density times gravity. That is the change of pressure with respect to x. It's mathematics, right? But don't worry about that. We are not going to use this differential form. So if you want to calculate pressure differences between 2 points, let's say here is x1, here is x2, the height is going to be h. Then I want to know the pressure changes between these 2 points. You can integrate this one from 1 to 2. Integrate this from 1 to 2. How you integrate that? dP dx. How you integrate that? Or you cannot integrate dP dx. You have to move one to the other. So I'm going to move dx to the other side. So we have dP is rho g and dx. Now you can integrate from 1 to 2. Do you remember how to integrate this one? Yes, it's simple. P2 minus P1. P2 minus P1. What about here? Do you know how to integrate this one? It depends on this one, the density. It depends on this one, gravity. So if you assume that density is constant, is gravity constant? Yeah, unless you go to the moon or Mars. If you stick to the Earth, gravity is constant. No? Yeah. So constant. When you have constant inside this in the integration, what do you do? Just take them out. Density times gravity. Now integration from 1 to 2 dx. Can you integrate this one? Yeah. x2 minus x1. P2 over P1 is density, gravity, x2 minus x1. What is x2 minus x1? H. So the P2 minus P1, that is the difference in pressure. The delta T, difference in pressure, is density times gravity times H. So this is how we determine pressure changes. So if you know this, the equation, that's the only equation that we are going to use. You can calculate how pressure changes, from the one position to the other. And let's talk about pressure, a little more, this coming Tuesday. Any question? No. And